एलडी।
हेलो सर, ये सर।
ମୁଁ କହିଦେବି।
ଆଜ୍ଞା ସାର୍।
ନା ମୁଁ କହିଦେବି ସାରଙ୍କୁ।
କଲ୍ କରିଦେବେ ନା
ନା
ପଚାରିବି
ନା
ସାରଙ୍କୁ?
କଲ୍ କରିବା ଯେ ତାଙ୍କୁ 245 କହିଥିଲି ଜଏନ୍ କରିବାକୁ।
ଆଜ୍ଞା ହଁ।
ତଥାପି ନାଇଁ ଇଣ୍ଟରଭ୍ୟୁ ମୁଁ କରିଦଉଛି।
ଇଣ୍ଟ୍ରୋଡକ୍ସନ ହଁ ସାର୍, କୋଉ ସାର୍ ଜଏନ୍ କରିନାହାନ୍ତି?
ନା ନା ମୁଁ ଇଣ୍ଟ୍ରୋଡକ୍ସନ ସାରଙ୍କୁ କହିଦେବି, ମାନେ ଯାହା କହିବା କଥା କହିଦେବି, ଇଣ୍ଟ୍ରୋଡ୍ୟୁସ କରିଦେବି, ସାର୍ ପ୍ରିଜାଇଡ୍ କରିବେ, ତମେ ଥ୍ୟାଙ୍କ୍ସ
ହୁଁ
ଦେଇଦବ ଆଉ।
हाँ ओके सर, थैंक्स थैंक्स गिविंग टाइम दे दी तो सर।
ହୁଁ ହୁଁ।
ओके सर, नो प्रॉब्लम।
है ऊपर आपका।
participant, Professor Dixit has joined. We'll start our session. Professor Dixit, sir, can you start the session?
Can you hear me?
Sir, it is audible, sir.
Yes. Fine, fine.
Sir, can you start the session, sir?
I have no problem. Yeah, I can start right away.
Okay, good afternoon to one and all. I beg excuse for some inconvenience in giving time span to Professor Dikir. So, from the side of organizing team, I am sorry. We beg excuse for that, and also we are thankful to the participant that you have managed the time to attend 5 minutes before. So now I request Professor Pradeep Dikshit sir to preside the session,
Okay.
and he will deliver the talk on electrochemical machining to create micro tool electrodes.
Okay.
Dikshit sir.
Okay. So, Dr. Dev, so as I mentioned that I have a meeting at 4. So
Sir.
I will try to finish this particular session by 4 up to 4:15 maximum. Okay.
Sir.
Yeah. So let me just share my slides. Let me see. Please let me know if you are able to share everything. Okay. So are you able to see the screen here?
Sir.
Yes, sir.
Oh, okay, great. Right. Okay, so let me just go back to one thing. Yeah, fine. Right. So once again, thank you, Dr. Dev. So yesterday I have presented my research work, which is happening here in Electrochemical Microfabrication Laboratory in IIT Bombay. And my today's talk is going to be a kind of a continuation in yesterday's talk. Okay. So yesterday we have mainly seen the glass micromachining by electrochemical discharge machining process, right? Which is so ECDM. Those who have attended this, can you please mute yourself, all of you? Yeah. Okay. So yesterday we mainly discussed about electrochemical discharge machining process. Okay. And today we are going to talk about some of the basic fundamentals and applications of electrochemical machining. Okay. So most of you who are from mechanical engineering, either your bachelor degree or master's degree, you may have gone through okay, something called as a electrochemical machining. Okay. So we are using this electrochemical machining for two purposes. Okay, and those objectives we are going to discuss in today's lecture. Okay. So first, what I will do that I will go through a bit kind of basic idea. What is the electrochemical machining? What are the basic fundamentals? What are the important parameters? Okay. As I said that most of you, I'm sure that you must be familiar with that. So once we gone through the basic fundamentals, we are going to discuss about the applications. Okay. So application of electrochemical machining, especially for micro machining domain. Okay. So I am using this electrochemical machining for mainly for two purposes, and this is for the size reduction. So whenever we require any kind of a micro tool electrodes, okay, we have to reduce their sizes. Okay, and for reducing the size, we are using this electrochemical dissolution. Okay, so ECD, okay, some people call it as electrochemical machining, some people call it electrochemical dissolution. If you are using for very precise application, then there is another term called electrochemical finishing. Okay, so most of these processes are fundamentally they are same. Okay, so I will show you the application, especially in two sites. One is what is known as an area array. Okay, so yesterday in ECD application, I have shown you that we are mainly using different kind of array tool. Okay, so area array tool, for example, 3x3, 5x5, and or any kind of thing. Okay, then we also have a line array tool. Okay, which is basically means that it is not going to be an area array, but it's going to be line format. right? So if the time permits, I will go through this thing. Otherwise, I am mainly going to focus about the area array things. Okay. And finally, as most of you may be aware, that this electrochemical machining is fundamentally used for smoothing surfaces. Okay. So if you have any kind of a rough surface and if you want to smoothen out, electrochemical machining is a suitable application. Okay. So this slide is basically describes the glass micromachining work which I had presented yesterday. Okay. So those who have attended it. Okay. So yesterday we have discussed mainly about electrochemical discharge machining, and if you recall, this ECDM is a hybrid combination of electrochemical machining and electro discharge machining. So basically ECM plus EDM. Okay. This is the main thing. Okay. Some of the results I have described yesterday. So for example, if you look at this picture here, this is a 5x5 array tool, okay, made by 5 array tool. And if you look at the dimension, okay, so dimension is roughly about 250 micrometer, okay. And what is the thickness of this glass workpiece? This is roughly about 500 micrometer, right? And if you see the right hand side picture, this is the same thing, but this is made by 2x5 array tool. Okay. And this is basically one here, and the array is shown here. Okay. On the bottom side, you will see the tool electrode, okay, which has been used to fabricate these through holes. Okay. So this tool here is made out of a stainless steel material. Okay. And the tip height is 15 millimeter. Okay. And if you look at the closer view of this tool tip, okay, here it is about 150 micrometers. So roughly about is going to be 1.15 millimeter, right? So, so far the results are quite promising. But if you look at the current trend, especially for MEMS packaging application, electronic packaging application, okay, so people are going towards reducing the opening size. Okay, so at present, the opening size is roughly about 250 micrometer, but industry, those MEMS industry, they want to reduce the overall size of these through holes. Okay, and what is the target? Target is roughly about 100 micrometer. It means that we need to fabricate through holes which are having a diameter of 0.1 millimeter. Okay. Now, if you look at this picture of ECDM, okay, if you want to create a smaller holes, naturally you have to fabricate, okay, a smaller tool electrode. It means that in order to having if you look at this dimension here, 0.15 is the tool size, which is resulting into a formation of 0.25. Okay, it means that the final opening size of the through holes is always more than the tool size. So if you want to create 100 micrometer holes, the first thing is that you need to make a tool electrode which is having opening size of 50 micrometer. And this is not a very easy task. Okay. So the through hole size will be decided ultimately by the tool electrode size. Okay. And if you look at this picture again, we are not talking about a single tip. Okay. We are talking about an array tool. Right? For example, this one is a 2x5 array tool here. Okay. So for 100 micrometer, opening size should be 50 micrometer and in this order. Okay. Now, just before proceeding, let me also show you that we have fabricated this kind of a tool electrode, okay, by using wire EDM process. So again, this slide is from my yesterday's presentation. Okay, these kind of a area array tool electrode have been fabricated by wire EDM process, right? And if you look at the process capability, okay, it has a lot of variety. You can create 3x3, 8x8, 2x5, or any kind of a this kind of a tool electrode, you can fabricate it. Now the question here is that we have learned that for creating a smaller holes, the tool electrode size should be in this order. Okay, but the fabrication of this tip size, tool electrode having a tip size, is very difficult. Using wire EDM, it's not possible. Okay, what are the challenges? Okay, the challenges will come because wire EDM involves a lot of high temperature process. Okay, so naturally it's a EDM process which is having a very high temperature in the order of 2000 degrees Celsius plus. Okay, so when you have this high temperature, you have a lot of thermomechanical stress. Okay, and if you look at this picture, okay, of the requirement, this length is very high, right? This is about 15 millimeter. Okay, right? And here tip size is very small. So what happens is that if you try to do that, okay, and try to create a very small tool electrode having size of 50 micrometer, there's always this tip has a bending issue. It means that the tip size do not remain flat, straight, they becomes bending. Okay. So because of this bending issue, it is the minimum size which we are able to fabricate by using iridium is 100 micrometer. Okay, right? Now you can also ask, okay, that what is the really need? Okay, so why do we need this 15 millimeter? Why not we can create, for example, 1 millimeter or 2 millimeter tip? Okay, height. So because if this 15 millimeter tip length is reduced to, for example, let's say 5 millimeter or 1 millimeter, then the problem of this bending will be resolved. Okay, because naturally this act like a cantilever beam. Okay, so the reason is that why do we need a high aspect ratio to electrode? Okay, so high aspect ratio means, okay, as I have explained yesterday, that it is going to be Z dimension, okay, divided by XY dimension. So in case of tool electrode, it is going to be tip length, okay, tip length divided by the tip size, right? Okay, so the reason is that, let me just show you. Okay, this picture is from the ECDM process. Okay, now in this experiment, we have utilized a 3x3 tool electrode, okay, having a tip length 5 millimeter. Okay, now what is happening here? You can see that what really happens is the following. Let me just indicate. Okay, so I'm just showing you the front view. Okay, we have a glass workpiece. Okay, so what happens is that because of the high temperature which is produced in the ECDM process, okay, here we have a water, right? Electrolyte, if you recall that we mentioned that we are using alkaline medium with water, right? So this water vapor is formed, and these water vapors basically, okay, goes like this. Okay, so from each side the water vapor is going up, and here at this cold place, they are forming this kind of bubble. So if you look at this particular video here, okay, if you focus this side here, you will find that you have this kind of a big bubble formation. Okay, so naturally what will happen here, after some point of a time, this water vapor, it's cooled down and it forms a bubble, and this bubble basically after some time it drop downs because of the gravity. Okay, once it's dropped, then this is a kind of a short circuit phenomena. Okay, the machining process automatically stops here. Okay, so it means that the process or electrochemical discharge machining process, it's not continuous in nature. Okay, it's basically interruptive, which is very bad for the overall performance point of view. Now what we can do is that in order to resolve this particular issue, okay, so what we have thought is that instead of going for this kind of situation here, okay, if we create a very long tip, for example 3 times longer like that, okay, this problem would be reduced. Okay, why? Because first of all, okay, this cold place is very far away, okay, and water vapor will take more time to reach towards the cold place, okay, which is basically base plate here, right? So if we increase the tip length from, let's say 5 millimeter originally to, let's say 10 to 12 millimeter, okay, then the problem would be reduced, and that is what we have done. So let me just show you another video. So how did we overcome about this particular problem? Okay, it's shown here in this picture. Let me just show you. Okay, right. So if you look at this picture here, okay, in this particular diagram, okay, this tip length is 15 millimeter. Okay, the problem of bubble entrapment is still there, but the frequency at which this bubble is dropping is drastically reduced. Okay, so you can see that the problem has not totally gone, but it has dramatically it is reduced. Okay, and this is the reason why we need to fabricate a longer tip. Okay, more than 10 millimeter. Okay, so it means that the tip length has to be 10 millimeter. This size has to be as small as possible. So for example, I mentioned to you that this is going to be 50 micrometer, right? Now we should find out, do we have any kind of a process, either conventional machining process or non-conventional machining process, which is able to fabricate a area array tool electrode, okay, having such kind of dimensions. Okay, so the same phenomena what I have just reported, okay, those still pictures have been I've indicated again because I have been asked to share these PowerPoint slides, and in PowerPoint you will not be able to see these video. So I have also summarized the phenomena which is happening on this side. Okay, so same phenomena from the video we have captured here, and this is what I was talking about earlier. Okay, so this is this kind of bubble phenomena. Okay, so if you use this 5 millimeter or shorter tip, the through holes which are formed, okay, are not nice. They are a lot of overcut. Okay, but if you carry out with longer tips, you will see that they all still have some kind of overcut, but the overcut has been drastically reduced. Okay, so these pictures clearly indicate that if you want to create a area array or large number of through holes at same time, you have to use a tool electrode which is going to having a very longer edge here. Okay, now the question here is that how do we create such kind of a tool electrode, okay, which is long, okay, in terms of length, okay, but very small in terms of a tool size. Okay, we cannot do any kind of a contact based machining, for example milling process or turning process. Naturally this is not possible. Okay, why? Because you can imagine that this is like a cantilever beam. Okay, if you apply any kind of force, what will going to happen? The stress is going to be very high, and most likely this thing is going to be damaged. Okay, so wire radium is the only choice. Okay, we are doing it, but even in wire radium, because wire diameter is typical, if you look at the diameter which is used in the wire radium process, either by molybdenum wire or brass wire, okay, they are typically 150 to 200 micrometer. Of course, there are smaller wires are also available, but those are very, very expensive. Okay, so if you use this kind of a wire electrode, because of the higher thermal stress generated during the process, okay, these tips will basically bend. So it should be straight like that, but naturally it is going to be bent like this. Okay, so what we have basically come out that it is not possible to create this kind of a tool electrode in a single shot. Okay, so what we have thought that we will first get this kind of a tool electrode by wire radium process. Okay, and then we will try to go for electrochemical dissolution. Okay, so idea here is that you fabricate the tool electrode. I'm just showing you a single tip. Okay, so this single tip, for example here, okay, it could be 150 micrometer. Okay, this could be 15 millimeter. Okay, same what we are doing it. Okay, and after some point of a time, if we do a controlled electrochemical machining, if I remove, let's say 50 micrometer from each side, for example, okay, we will be naturally removing this material by electrochemical dissolution, and we'll get a final tool electrode having a dimension. Okay, so we try to do this kind of a combination of wire radium plus electrochemical dissolution to get the required sizes. Now the question here is that why we have chosen electrochemical dissolution? Okay, so of course electrochemical dissolution has a lot of advantage. The very first advantage is that this is going to be room temperature process. Okay, so typically all the electrochemical machining process is performed at room temperature or a slightly higher temperature up to 40-45 degrees Celsius. Okay, so because of the room temperature, we do not have any kind of a thermomechanical stress, because okay, it's a very, very low temperature process. Okay, it is possible to go for a controlled atomic level dissolution. For example, if you want to remove, let's say, a few nanometer, okay, fundamentally, in principle, this is possible by using a very small current. Okay. Second thing is that besides the size reduction, you can also improve the surface smoothing. Okay, so as you know that in EDM process, right, because this is a high temperature process, there is a lot of surface roughness. Okay, and this surface roughness, if you want to reduce it, okay, you can use electrochemical dissolution or electrochemical finishing process. Right. Now the challenge is that, okay, so all these things which I just mentioned, they are fundamentally possible. Okay, in theory you can do that, but when you try to go in a real application, okay, you have a lot of challenges. The very first challenge is that, can we get a uniform dissolution? Okay, what do you mean by uniform dissolution? So if you look at this picture which I'm drawing now, okay, this is my initial profile. Okay, this is the final profile here. What I want is that I want to remove 50, for example, in this 50 micrometer dissolution from all the points. Okay, so this is what we define as a uniform material dissolution. But when you try to do in the experiment, you will see that uniform dissolution is extremely difficult to obtain in a real life situation. Okay, the trick here is that, okay, how do you control the current density distribution? How do you control the current lines in case of electrochemical machining process? Okay, so I think I will skip this slide. Most of you are familiar with the applications. Okay, currently it is used for example, surface smoothing experiment. For example, if you look at this case here, where we are using a biomedical application, nickel-based alloy. Okay, and this smooth surface is obtained by electrochemical dissolution process. Okay, so I will skip it. Yeah. So most of you are familiar with electrochemical machining, so I will try to skip it couple of slides. But important thing is that you know that electrochemical machining can only be used for those material which are electrically conductive, right? So we have an electrochemical cell. We will have two electrodes, right? And the electrode where you want to remove the material, you need to connect to the power supply, positive terminal, okay? And then you have a suitable electrolyte, okay? And material will be basically removed from this particular electrode by electrochemical dissolution process, okay? So in principle, whatever material, whatever hard material you have, for example, in aerospace industry, we are using a lot of nickel-based super alloy, right, in Inconel, which are very, very hard. Okay, so by conventional machining process, it is extremely difficult to remove the material. But when you try electrochemical machining process, as long as material is conductive in nature, okay, you are going to simply dissolve that particular material. Okay, so this is going to be a hardness independent parameter. Okay, similarly, reverse of ECM. Okay, so if you change the polarity of the electrochemical machining process, okay, that process is called as a electrodeposition, or we call as a electroplating. Okay, so electroplating is one of the most widely used process in electronic industry. So all in your mobile phones, your tablets, your computers, okay, you are using a lot of ICs, integrated chip. You are using a lot of PCB. Okay, so all those PCBs in ICs, whatever interconnect you have, okay, all the copper is mainly deposited by this particular method. Okay, so let me okay, so idea here is that in a case of electrochemical machining, okay, you have two electrodes. Okay, workpiece is connected to positive polarity because you want to remove the material, okay, by converting them into metal ions, right? Then you have a suitable electrolyte, okay, and electrolyte basically pass through the medium, okay, and it removes the sludge formation. Okay, this is one of the key aspects which I'm going to talk about a little bit later. That removal of the sludge is very challenging task, especially in a deep features. Okay, so the important feature is that two electrodes and electrolyte, and also you have to maintain a kind of a consistent gap, okay, because this gap is going to be very, very important again, okay. If you do not maintain a constant gap, machining process is going to be affected, right? So now look at the fundamental of this electrochemical machining process, okay. So this in electrochemical machining process, the material removal process is governed by Faraday law, okay. Now there are two laws, okay, Faraday law, those who may be familiar in electrochemistry. So there are two laws. One says that in any kind of an electrochemical dissolution process or electrochemical plating, okay, mass of the material which is deposited or removed, it is going to depend upon charge. So, okay, so whatever the mass which is going to be removed, it will depend upon the overall charge which is going to be provided during the process, right? So this charge is nothing but a current which is passing through multiplied by the time, right? This is the first law. Second law says that this one mass is also going to depend upon the chemical equivalent weight, okay, Z. So chemical equivalent weight, okay, which is nothing but a atomic weight of that particular material, okay, divided by how many number of electrons are going to be transferred, okay, number of electrons which are going to be transferred. What does it mean? So for example, if you look at iron, right, when you put iron into an electrochemical cell, okay, iron makes this one, but also in some cases it makes this Fe3. So this is ferrous and ferric, okay. So these numbers, these are the number of electrons which we are going to transfer during the electrochemical reaction, right? Now if you look at the practical example of how we do the machining of iron based material, okay, so so what kind of electrolyte we are using? So NaCl and another is more popular is NaNO3, okay. These are the two salt solution which are basically dissolved in DI water and generally used as an electrolyte, okay. So what happens is that there are several reactions, okay. So H2O, for example, it forms H plus and OH minus, okay. NaCl forms this thing, and these reactions are reversible in nature. It means that there's going to be the salt is going to be like broken down into ions, and ions will also have a recombination mechanisms, okay. So this iron, what is happening here, iron basically forms this Fe2O3, and this Fe2 will going to combine with this and also in some cases in the chloride, and they will form this kind of ferrous oxide, and in some cases this ferrous chloride also, okay. So whatever is this reaction product, we are calling them as a sludge remover, okay. This is sludge is basically kind of a chemical reaction product, okay. So what is happening here, that we are removing the material by converting the pure form of metal into ions, and those ions are going to be combined with the chemical component of electrolyte, and they will form a sludge removal, okay. So this is basic fundamental concept behind the electrochemical thing, okay. So if you combine then both of these two laws, okay, the first M is going to be Q, which is nothing but in another word, this is going to be IT, and the second is going to be M is going to be Z, which is nothing but atomic weight by a number, okay. So you will get this thing Z, I, T, and this is going constant. If you remove this, you get a Faraday constant, right? So this is the very basic Faraday law, which will give you a theoretical amount of a material dissolution, okay. Now in reality, what happens here, if I go back to this slide here, we also have the water electrolysis, okay, H plus, okay. So H plus basically it will go towards the cathode, where it will find an electron, and it is going to basically form a hydrogen gas also, okay. Similarly, we also have oxygen gas, which is basically formed a little bit in quantity. So the idea here is that whatever energy, whatever electrical energy which you are providing through the using this power supply, okay. So theoretically, you are providing the total power per second, okay, is going to be VI, Okay, so not the entire part of the input electrical energy is going to participate in the material dissolution. Some of the part is also going to have participate in this kind of a reaction, which is non-productive, because our main interest is finding in the material dissolution. Okay, so that's why there is a term called current efficiency. Okay, so it means, so if I say current efficiency is 90 to 99%, what does it mean? It means that if I have 90% current efficiency, okay, it means that if I am providing, for example, let's say 100 joule of energy, okay, then 90 of joule is going to be participate in the material dissolution, and 10% is going to be in other secondary reactions and so on. Okay, so generally in case of electrochemical machining process, the current efficiency lies between 95 or more than 95% here. Okay. So now let's look at this Faraday law. Okay, this is what we have learned in our electrochemistry classes and so on. But now the question here is that, does this Faraday law provide all the necessary information? Okay. For example, does it talks about position dependent behavior? Okay, what does it mean? So for example, if I'm using, let's say this, I have area array tool. Okay, so I'm just showing you the front view. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the 9 tips, right? So if I keep this kind of a area array tool electrode, which is shown here in this picture, let me just show you. Okay, so this is this picture is before machining process, right? Before we put in a electrochemical machining. Okay, so for example, if you look at this picture, the tip size is 130 micrometer. Okay, at a distance of 600, this is 200 micrometer is the width, right? Now, if I put this tool electrode in an electrochemical machining process, okay, so this image is after machining. Okay, this is after ECM process. Okay, now what do you see? You can easily see that before and after, you can see that the tip has become very, very sharp, right? This is a close view. Okay, so the tip has become really, really sharp. If you compare it, for example, this thing, this is really, really sharp here. Okay, so it means that electrochemical dissolution is taking place, right? But more importantly, if you look at this picture here, right, you can see that all the tips are not at same level. Okay, you can see that this tip, okay, this one, let me just remove this line so that you guys can see clearly. Okay, you can easily see that some of the tips are shorter, okay, some of them are longer. Okay, and this tip, which is the longest one, okay, this tip is present in the center of area array. So for example, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So this is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so the longest tip which you will see here, this belongs to the center one. Okay, and the shortest one, these ones, they belong to the outermost thing. Okay, right? So this is the experimental result. So it means that in electrochemical machining process, we also have something called location dependent behavior. Okay, and this behavior is especially significant when you are doing etching, especially of a big large area array electrodes. Okay, if you have a single tip, it does not matter. Okay, but if you have a kind of a close proximity, okay, then you will see this kind of a behavior. Okay, so in large area array connections, okay, this particular behavior is very dominant. Okay, so the question here is that, how do we get uniform material removal rate? Okay, now this observation is more significant for us because up to the best of our knowledge, okay, we are the only research group right now working on a area array tool electrodes. Okay, we are trying to create multiple through holes in glass. Okay, for that we require this tool electrode, and up to best of our literature research, okay, we are the only, or maybe few more might be there, but we have not come across them. Okay, right? So this was the thing. So our objective was to get a uniform resolution, okay, especially in this case. Now you can always ask me that what is the problem? Okay, so for example, if you look at this scale here, from this point to this point, this is roughly about 3000 micrometer or 3 millimeter, right? So if you look at between this tip and this tip, okay, the gap is not going to be more than 100 to 200 micrometer, okay, which is not very large one. However, if you have such kind of tip electrodes, they will create problems. What kind of problems? Let me just show you. Let me just, I will probably, okay. Yeah, I think this slide would have come later on, but let me just show you first, okay? So for example, I had indicated here, this is before ECM process, okay? Tip size was so and so. After ECM, it becomes like that, okay? If you use this tool, electrode for ECDM, okay? So these two electrode were used for ECDM or electrochemical discharge measuring process, right? So the tips looks like this, okay? Now, if you look at closely, you can see that some of the tips, especially 1, 2, 3, and 4, they are still very sharp, just like this. Okay, but other tips 1, 2, 3, and 4, okay, they are still having a sharpness, but you can see some kind of a blackish issue, right? Okay, but the tip which was located at center, okay, it has bended. Okay, so what does it mean? It means that this tip, which was the longest in nature, okay, it has come in contact with the glass workpiece, and that has caused it bending. Okay, so these are the through holes, or these are the, I would say, holes which has been created by this tool electrode, right? So you can see that, okay, those tips which were sharpness, okay, for example, the cornermost tips, 1, okay, this one, 2, so let me say 2, 3, 4, 5, 6, 8. Okay, so you can see that all those corner tips, okay, holes were not formed. Why they are not formed? Because those tips, they were not coming in contact with the workpiece, and they did not participate in the machining action. Okay, the only tips which were in contact, okay, 5 impression were formed, and which is these two, 1, 2, 3, 4, and 5. So it means the message is very, very clear, right? It means that if you do not have any kind of a uniform tip electrode, okay, they will create problem in ECDM machining process. Okay, so I hope that this thing is clear. Okay, so let me go back to this thing. So this is one of the challenge and one of our objectives. Now, what are the other challenges? Okay, in case of ECM, so I've already mentioned to you about uniform resolution. Okay, second one is very important, is that if you want to create any kind of a high aspect ratio features, right? Again, if you want to create any kind of, let's say, holes or electrode, okay. So in case of electrochemical machining, they will create some kind of a problem. Okay, so the reason is very simple. The reason is that, okay, so this picture is shown here. So what will happen here? So this is the tool electrode, which is basically, let's see, this is a negative polarity here. Okay, this is a positive. Okay, you want to do some kind of machining. Okay, so when the depth is shallow, okay, so red particle here, they indicate the sludge. Okay, right. Okay, so when the depth is shallow, the sludge removal is easy. Okay, relatively easy. Okay, when the depth has gone from this to this, okay, the sludge removal is getting a bit more difficult. And once you cross a critical depth, what happens is that sludge is not able to come out from the machining zone, and it get redeposited on the side walls. Okay, it means that machining process will slowly stop. Okay, so if you want to create any kind of a high aspect ratio features, it is very, very important for you to remove this sludge. Okay, now the question here is that what we can do. Okay, So the first trick what people do, they start rotating the two electrode. So that this is two electrode, but we are providing this kind of a rotation. Okay. Now when you are rotating it, it means that at this particular location, okay, you are having this kind of a centrifugal force, right? Because of this particular rotation n. Okay, so it means that from in this zone here, okay, you are having some kind of extra forces which is responsible to throw away all the sludge outside. Okay, so this is one of the trick people do. Now the only limitation in this particular case is that it is only used or useful for a single tip electrode, right? If you have an area array, okay, you cannot use this thing, right? So if you have an area array or something else, then the only option is for you is to provide some kind of a vertical ultrasonic motion. Okay, so this is why this kind of a technology or a process is known as a ultrasonic assisted electrochemical machining, where the idea here is that we are providing some kind of a small amplitude. Amplitude could be from 10 micrometer to 50 micrometer, but at a very high frequency. The frequencies should be very high. So what does it mean? It means that within a second, okay, we are going to have 20,000 vibrations. Okay, so once you create this kind of a vibration, okay, what happens is that you are basically forcing the sludge to come out. Okay, at same time you are also generating the pressure wave, and that pressure wave is responsible for both for sludge removal and also assist in the material removal process. Okay, so this is some of the things where people are currently working on. Okay, so I'm not going to talk about this thing here. I'm only going to talk about how to maintain a controlled electrochemical dissolution. Okay, now all the experiments which we have carried out, which I'm going to present, have been performed on this. This is an in-house setup here. The process is very simple again. Okay, so we have this XYZ machine, okay, which is machining chamber, and this is a normal power supply, okay, which is a like normal DC power supply. You can also use pulse power supply, okay, and then we have a motion controller and so on. Okay, and this picture which is shown in the inset, okay, this picture is about a single tip. Okay, so single tip electrode, and we are trying to reduce the size reduction. Okay, size reduction. Okay, so this is a tool electrode which is connected to the positive supply. This is going to be a counter electrode which is going to be the negative supply, and we are using it. Okay, so all the experiments and whatever we are going to show you today is performed on this in-house built-up setup. Okay, so when we started this kind of work, so we started with a single tip. Okay, and then we moved to a area array tool electrode. Okay, now for performing the single tip, okay, we had chosen this normal needle. Okay, so this picture here, this is normal cloth stitching needle which you find in any shop. Okay, and this cost is very cheap. Like if you spend 20 rupees, you will get a packet of 10 needles. Okay, so this particular needle, okay, the material is this is a high carbon steel material. Okay, and on top of the tap they are putting some kind of nickel coating. Okay, now what we have done is that, so if you look at typically this kind of a needle, they're very sharp, right? This is a conical tip shape. Okay, so what we have done, so we have done our experiment, our analysis on a conical tip, and in some cases we had done some grinding, okay, to get this kind of a cylindrical shape needle. Okay, so with the same kind of a needle, we have also created a cylindrical tool electrode. Okay, now the objective was very simple. That if you look at the typical diameter, okay, so this opening or opening diameter of this needle is 600 micrometer. Okay, there are different kind of needles which are available in the market. Okay, we are using this cheapest one, and it has having a diameter of 0.6 millimeter. Okay, the objective was to perform, okay, and reduce the size to less than 100 micrometer. Okay, so here is the initial results. Okay, and here is the final result. Okay, I'm just showing you right now. Okay, so this is fine. So our objective was to reduce the diameter to less than 100 micrometer. Okay, now the question and objective was that we need to get a uniform. For example, if you look at this case here, I'm trying to draw the initial shape. Okay, for a cylindrical tool, this was the tool. Okay, and we wanted to basically get a uniform dissolution. Okay, so the experiments which were performed for a NaCl or 5% sodium chloride. Okay, so before going for directly going for experiment, we have also tried to do some analysis, some numerical simulation to find out that what is going to be the distribution of current density, right? So if you recall by the Faraday law, okay, it is going to be Z, okay, I, T, and F, right? So basically, it is going to be a function of a current. So current is going to be the most important function here, right? And if you look at the actual case, if you decipher this left-hand term here, okay, M is going to be the density, okay, and multiplied by volume, and volume is going to be the area, surface area, and the height thickness reduction, right? So if you look at this particular term here, okay, ultimately what happens here is that this H is going to be Z, I, T, which is time, F is going to Faraday constant, and let me just say it here. So from this side, it is going to be rho, which is going to be density, okay, and the surface area in this case, right? So our objective was to find out this thing, that the H should remain throughout the same. And in order to predict the behavior, that we need to find out what is going to be the current density distribution. Okay. So we, my student have taken this COMSOL commercial software, and we find out that what is going to be the distribution here. Okay. So we have figured it out, okay, which is also a known knowledge, that in any case of either cylindrical tool or in case of a conical tool, okay, the current density is highest, okay, on this kind of a corner point. Okay, so at this tip, this is some of the area where current density is going to be the highest. So it means that if you carry out the electrochemical machining from this point, okay, in case of cylindrical tool, at these locations, the material removal rate is going to be higher. In case of conical tool electrode, this is going to be higher here. It means that if I choose, let's say, 2 points, for example, point number A, okay, and point number B here, right? So in practical ECM, at point number B, the material dissolution rate is going to be higher than point number A. Okay, but if you recall Faraday law does not talk about location dependent material removal behavior. Okay, this is totally dependent upon how the current density is going to be concentrated at different kind of points. So it is very, very important for anyone to find out what is going to be the distribution of the current lines in any kind of a electrochemical dissolution process. Okay. So we have started doing experiment, okay, mainly, and so this is the very first task is to find out what is going to be the VI characteristics. Okay, so in any kind of electrochemical machining process, okay, we have something called overpotential here. Okay, so overpotential means that you have to apply a certain potential, okay, only above that machining will take place. Okay, so for example, overpotential typically lies between less than 1 volt for most of the conductive application here. Okay, and this is how the current versus VI characteristics in case of electrochemical machining is present there. Okay, now I have mentioned to you that this is going to be a HCS high carbon steel. Okay, on top of that we have a small nickel coating. Okay, so when we have done some experiments, okay, so this is some high-speed camera images. Okay, you can see that this is a 0 second. Okay, and we have tried to capture the photograph with respect to different time intervals. You can see that there is going to be some kind of a deposition here. Okay, so at 0 second, there was some width here, but after 240 seconds, which is going to be 4 minutes, okay, you can see that this electrode has basically become thick, okay, and this is basically a kind of a nickel chloride material, so which is basically formed as a sludge, okay. So this nickel chloride is coming from the nickel coating which was present on top of the electrode, okay. So that is one of the finding we have, that if you do not remove this kind of a nickel coating, it is going to cause problems during the machining process here, okay. So let me just show you that how are the results. So we have taken 3 values of voltage, okay, 2 volt, 4 volt, and 6 volt, and these are some of the pictures at different time intervals, right? So idea here is that you can see that in some cases the surface is very smooth. In some cases the surface is black, okay. This black film is the same nickel chloride film which is basically present in this case, okay. So it indicates that if you do not remove this nickel chloride, okay, or in other word, if you do not remove the sludge efficiently, okay, you are going to have a problem during the electrochemical machining process, okay. At same time, you can see that if you look at 6 volt, right, 6 volt, you can see that, okay, from 240 seconds, okay, it was there, and 360 seconds, this complete part is basically etched away. Okay, so it means that you need to use some kind of a smaller value of machining voltage. Okay, so from our experiment, we had figured it out that 4 volt was giving us the enough sufficient value in which we are getting a controlled electrochemical dissolution. Okay, this slide basically shows as a comparison between a simulation, okay, and the experimental data, right? So if you are able to see that this dark blue, okay, line is a basically simulation data, and this dotted black line basically indicates the experimental values here. Okay. So of course, as I have also pointed out earlier also, that in most of the practical cases, there's always some kind of a difference between a simulation result and experimental results, and it is the job of a researcher to find out what are the valid reasons behind why there's some difference between a simulation and experimental results. Okay, so for our case, it was very difficult for us to find out the current efficiency. Okay, so current efficiency, we have no idea. So we have taken from the literature value, we have taken, for example, 95%. Okay, but it appears to be that this value was not really correct, and because of that, we were getting some kind of difference between simulation and experimental results here. Okay, so after doing a lot of kind of optimization work, we were able to get this kind of a feature. So here is the results. Okay, so this is a initial needle. Okay, having a diameter of 600 micrometer. Okay, this is if you use a 4 volt, okay, up to 11 minutes, this is the value. Okay, so we had kept up to 10 millimeter immersion depth. It means that during the machining process, right, this was the immersion depth. Okay, this was the depth up to which we were having electrolyte. Okay, that's why this part is still intact, and machining only takes place from this particular region. Okay, so by doing a bit more optimization, okay, we were able to achieve our objective. Okay, for example, here the diameter is 80 micrometer up to length of 7 millimeter. Okay, here the diameter is going to be 120 micrometer. So it means that by using a controlled electrochemical machining method, it is fundamentally possible to achieve a micro tool electrode. Okay, however, at this particular stage, it is still a single tip electrode. Okay, we have not talked about any kind of area array. Okay, this was still a single tip electrode, right? So so this electrode which we have formed, okay, that was used to in ECDM application. So this is some of the results. Okay, so this was the single tip electrode. We call it a single electrode. Okay, this was used to create this kind of a feature. Okay, and as you can see that, okay, at the bottom, the size was very, very small. Okay, so here the tip diameter is going to be 110 micrometer. At the top, it is going to be 240 micrometer. Okay. So what happens here? Let me just indicate here so that this is the profile I'm drawing here. Is about a tool electrode. Okay. So you have to remember that the tool electrode, basically it's a bare. Okay. So as the tool goes down, okay, because of the discharge happening from the side walls, there's always this kind of tapering is there. Okay. So in order to find out the effect of the reduced size, we have to look at the bottom diameter. So bottom diameter is 110. Okay. Right. So this is the sum of the results. So it means that fundamentally we can use electrochemical machining process. We can reduce the size. Okay. And those reduced size can be used for making smaller glass via. Okay. But the question here that can we repeat this experiment for a like area array tool electrode? Okay. So now let me just go to the main thing, which is the area array tool electrode. Okay. So for example, let me just draw you the picture here. Okay. So this is an area array tool. So I have just shown you the front end. There's going to be also going to be 3 tips like that. Okay. So now if you look at this case, if you recall the discussion today and also yesterday, what happened? So we are making this particular tool electrode by bi-radium process, right? So we have a bi-radium thing here. So all the tips are having the same height. Okay. Now if you use the tool during the ECDM process, because of the high temperature, okay, the temperature goes beyond 2000 degrees Celsius. Okay, there's always going to having some kind of a tool wear. Okay, so we have noticed that even the tool wear is not uniform, not consistent, not same. Okay, so if you look at the profile of the tool electrode after ECDM process, okay, all the tips are not going to be of the same height. Okay, and this will create a problem. So what we have tried to do, that what we are doing it here, that after ECDM process, okay, we are again doing the second bi-radium process. Okay, second EDM to cut, okay, to remove this particular part here. Okay, so all the tips are going to be of the same height. Okay, so this is what we are doing it in order to reuse the tool. But the problem is that if you look at this tool here, although all the tips are having the same height, but if you look at the width here, right, this width is not same as the width which was before. Okay, so this width was here, this width is going to be changed, right? It means that if I use this tool electrode, the size of the through holes is going to be different. Okay, so now what we are doing here, that after making this kind of bi-radium process, we are again doing electrochemical machining process so that we can basically get the same width as before. Okay, so I hope that this thing is clear. So our objective is that we have to obtain a tool electrode which is having the same height. Okay, all the tips should be same height, but at same time the width should be also be same. So for example, this width which is indicated here is T2 should be same as the T1 here. And in order to do that, we are using electrochemical degeneration process. Okay, right? So I think I have covered this slide before. So the problem is that if you do this ECM process, okay, all the tips will not be having the same height. Okay, so we have observed this thing, that this phenomena is taking place, that all the tips are not having the same height. Okay, so in order to solve this kind of a problem, how to get the same height, okay, what should we do? So we have focused on the 2 aspects. Okay, so I hope that this particular problem statement is clear with everybody. Okay, so if all the tips in an area array tool electrode is not of the same height, okay, what would happen? Many of the tips is not going to participate in the machining process, and as a result of that, these through holes will not be formed. Okay, so you can see that from the previous example that if you have this kind of a tool electrode, we are not going to having any kind of a machining. Okay, so in order to get a consistent machining, okay, one of the fundamental requirement is that all the tip should be of the same height. Okay, so maximum allowed variation, okay, in the tip heights has to be less than 50 micrometer. This is a strict requirement from the electrochemical discharge machining process. Okay, right? Now you can ask me, okay, that why we are not getting this kind of a consistent, what is the reason behind that? Okay, why we are not getting all the tips on the same height? Okay, so let me just okay, fine. Okay, right. So what we have observed here, what we have investigated, and after extensive experiment, what we have concluded is that the size of the electrode, okay, there are two important, very important terms. Okay, one is known as a shape of the electrode, shape, and second is going to be the size of the counter electrode. Okay, so for example, in this case, okay, this is a workpiece, so this has to be positive, right? So the counter electrode is going to be, whatever we are using it, this is going to be a negative cathode, right? So the two important terms which are basically responsible for getting uniform resolution is shape and size. Okay, so let's talk about the first, the size of the two electrodes, right? So mostly in case of electrochemical machining process, we are using a flat plate electrode. Okay, flat plate electrode means that either we are using this kind of a flat plate electrode either in the vertical configuration or in the horizontal configuration. Okay, so we have seen here is that okay, so before that, let me just indicate the nomenclature so that you guys are clear. Okay, so this is the 3x3 tool electrode. Okay, the tips are basically mentioned by 1, 2, 3, 4, 5, 6, 7, 8, 9, basically in this order, right? Something like this. Okay, so the tips which are indicated at the cornermost are E1, this, and this, which is basically shown here in a brown color. The centermost tip is indicated by E5. Okay, and then there are tips which is present at the outer periphery but in the center. So they are E2, E4, E6, and E8. Okay, so what happens is that the maximum variation, okay, maximum variation in the material resolution comes from the center tip and the cornermost tip. Okay, so this E1 and E5, for example, the variation is in this centrally located tip, the material resolution rate is always lower. In this case, it's always higher, right? So if we find out the machining rate between E5 and E1, okay, if they are same, we will call it as a uniform material resolution. Okay, if in another word, E1 minus E5, okay, if it's 0, then we will say that in this area at a tool electrode, we have a uniform material resolution. Okay, so our objective was to see whether the difference between the center tip and cornermost tip is 0. Okay, so these are some of the simulation picture. This picture basically indicates the before machining, and this indicates at the after machining. Okay, now if you look at closely, you can see that the shape, okay, shape of the tips is changing. For example, if you compare with the central tip, which is E5 here, okay, you can see that the center tip has already been dissolved. Okay, right, this one cornermost, but nothing has happened in the center. They're almost basically more or less same. Okay, only thing is that this basically represent that this is going to be a pyramidal outer boundary, This basically indicates that this is the central tip, okay, and this is the edges. This is the top view here, right? So if you look at this one versus this one, you can see that this has become smaller, okay, this has become also smaller, something like this. But the one which is present at the cornermost, they have drastically changed, okay. So what we have seen here, okay, that first of all we have tried to investigate that how does the counter electrode size is going to affect the material dissolution, okay. So counter electrode in this case, this is nothing but cathode, okay. Size means that, okay, right. So let's look at this picture again, okay. So this is a basically showing 3x3 tool electrode, okay, and the size of this tool electrode is going to be 3.22 millimeter. So for example, let me just show you in picture, okay. So from this to this edge, this is 3.22 millimeter, okay. So what we have done is that we have taken three cases, right? So we have a anode, which in this case positive one, okay. We have a counter electrode which is connected to a negative polarity here, right? So we have taken three cases. The first case, we have kept the cathode area smaller than the anode. Second case, we have taken same, and then third case is going to be, right? Now we have plotted, we have done simulations, we have plotted the results, okay, based on this thing, okay. So as I said that our objective is to obtain E1 minus E5. E1 indicates again the cornermost tip which is present in the corner, okay. So that is E1, and centrally one is E5, okay. I hope that this thing is clear, right? So we have taken several cases, for example 1.25 millimeter to 10 millimeter. This is the shape, this is the size of the counter electrode, okay. And with time we have done the simulation and we find out that what is going to be the variation, okay, and the results are plotted here. So when this tip, when the counter electrode is larger than the 3.22, which is the actual size, which is going to be this case, you can see that the E1 minus E5 is positive. What does it mean? It means that the etching rate in case of the cornermost tips is much higher compared to the centrally located tip, okay. Now when we have seen the opposite term, for example if you look at this case which is 1.25, okay, so which is this case, okay. So here the trend was opposite, okay. What is happening? So even cornermost tip has a lower etch rate compared to the centrally located tip, okay. And the best result, okay, because our objective is to get E1 minus E5 is 0, which is this condition, okay. Our objective was to get result as close as possible to this one, okay. So we have seen that when this size of the cathode and size of the anode is exactly same, okay, the result are best, okay. Now the reason is very simple, okay. So if you look at this thing, what will happen? The current lines, okay, let me draw the current lines from the positive side, okay. So current lines basically are indicated in this term, okay. Okay, so this is going to be the current lines, okay, they're all going. So you can see that those current lines are going to be converged from the anode towards the cathode side here, okay. But in this case, if you look at, sorry, 1 minute. So in this case, when the size is same, all the current lines are basically parallel in nature, okay. And if you look at other side here, current lines is going to be converged because this tip is going to connect from this extreme condition, right? So they are going to be basically about a diverging, okay. So you can see that depending upon their convergence, where the concentration of these current lines are going to be highest, material dissolution is going to be the more or highest in those cases, right? So from this particular simple experiment, we have figured out that in order to get a uniform material resolution, the size of the cathode and anode has to be same. Okay, that is the kind of conclusion we have got. Okay, but the problem is that, especially for those researchers who are working on a micro machining area, right? So for example, okay, so 3.22 is very large. Okay, if you have to make any kind of a practical application, you can imagine that the size has to be very, very small, right? So in this thing, we also need to first fabricate this counter electrode. We also need to provide the electrical connections. So in many applications, this is not possible. This is not possible to utilize such a small cathode. Okay. So from practical application, such kind of electrodes are having difficulty to be really implemented. Okay. So we thought that can we take, let's say, relatively larger size, but can we do something else to get a uniform resolution? Okay. And this is where we had focused on changing the shape of the counter electrode. Okay. So earlier we were focusing on the size. Now we are going to focus on the shape, right? So this one, the workpiece or the area array tool electrode was same. Earlier we were using a flat plate electrode. Okay. So we decided not to use flat plate electrode, but to see the effect of the shape. So we have utilized a spherical, okay. This is a what we call as a truncated pyramidal shape. Okay. This is a pyramid. Okay. And then we have to utilize a conical shape electrode. Okay. Right. So we had played around with all these things. What is the shape of the electrode? Okay. So here in this table are the data for all these counter electrode shape and size. Okay. So for example, spherical one. Okay. We have taken 10 millimeter, 5 millimeter, 4 millimeter, truncated pyramid. We have just taken all these examples. Okay. So once we have investigated about the shape, okay, the results were quite very encouraging. Okay. So here again is example. This is again the some simulation results. Okay. This is a 3x3 tool electrode which you are observing it. Okay. And here we had kept the different kind of a cathode shape. Okay. And we have investigated that what is the current density, okay, in each of the tip. Okay. Mainly we are focused on the cornermost tip, okay, E1, and the centrally located tip at E5. Okay. So if the current density distribution in these tips are same, then of course material resolution is also going to be same. Okay. So now we have got very, very encouraging results. Okay. Results are basically shown here in this picture. Okay. So this is before processing, before doing any kind of electrochemical machining. All the tips are of the same thing. So this black picture indicates about E5, which is centrally located tip. Okay. Now, if you look at this, this is a with flat plate electrode, conical electrode, and spherical tool electrode. Okay. So after this kind of interval, okay, so we have seen that the results obtained with a spherical shape counter electrode was better than the results obtained with a flat plate electrode. Okay. So this one basically was giving us a better results, especially when the size was large. Okay. So this just to summarize this work here. Okay. So what we have done, again, this is going to be y-axis is basically indicated E1 minus E5. Okay. This is x-axis indicates about the time behavior. Okay. And three tips, spherical, flat plate, and conical tips were basically chosen here. Okay. So if you look at this kind of a summary, okay, what is the result obtained? That after 12 seconds of electrochemical machining, okay, the E1 minus E5 is touching the zero line. Okay. At same point timeline, okay, conical electrode was slightly better, but flat plate was totally off. It means that if you want to utilize for any significant etching, okay, you cannot use a flat plate electrode. This was our conclusion. okay, you have to go for a spherical shaped electrodes. Okay, so that is one of the thing. So after doing this kind of simulation, we have again done the experiments on the same tool. Okay, so this is a flat plate electrode. Okay, this is a conical electrode, and this is a spherical shaped electrode, which is basically shown here. So this is a counter electrode. This is the area array electrode. Okay, and before and after machining, we have performed the experiments. Okay, so the results are basically shown here. This is a flat plate electrode. Okay, now if you look at the bottom picture, the difference between a centrally located tip and the cornermost tip was 131, right? And if you use a conical tip, the difference was reduced to 50 micrometer. And in case of a spherical thing, the difference between centrally and outermost tip was 30 micrometer. So it clearly indicates that if you want to utilize a larger electrode, okay, you can use a spherically shaped electrode. Okay. Now the reason is also very simple. Okay. Now if I draw a picture here, this is a spherical one, right? Now this is the let me just so idea here is just to play around with the electrochemical condition. Okay, so these are the tips. Okay, right? Okay, so from simulation we already know that the outermost tips which are present, they have a slightly higher current density. Okay, but if you look at this picture here, okay, because of the curvature of this counter electrode, okay, so for example, let me call it as a E1. Okay, this one is E5, centrally located tip, right? So you can see that the gap between the centrally located tip electrode and outermost electrode is not the same. Okay, so this gap, okay, is not the same. So gap is larger here. Okay, gap is smaller here, and this gap is ultimately, if you recall your basic electrochemical machining process. Okay, so if the gap is large, what is going to happen? The resistance is going to be large, right? And resistance is going to be large means that at same voltage, the applied current is going to be smaller one. And smaller current means that the material removal rate is going to be smaller one. So by using the spherical tool electrode, whatever was the effect of the current density, it was basically neutralized by using the different gap by using a spherical tool electrode. Okay. Right. Let me see. So here is again just to show some of the experimental results. Okay. So this is a flat plate. This is a spherical shape thing. Here, let me go back here. Okay. Now this is the obtained one. Now it is not visible probably to some of you, but if you look at closely, again this centrally located chip here. Okay. It is slightly larger compared to the uniform tip which was obtained by using spherical tool electrode. Okay, right. So let me see how much time we have. Okay, another. So I'm running a little bit of time. So I will try to skip a few slides. Okay, just to will try to provide you a summary of the results. Okay, this is again the same picture from the obtained one. Okay, after that we have also investigated the effect of the pulse parameter. So we have seen that effect of the shape of the counter electrode. We have seen how the sizes affects. Okay. After that, we had done DC versus pulse. Okay. So it is basically a kind of a known knowledge that compared to DC continuous power supply, okay, pulse power supply will always give you a better results. Okay. But we again try to investigate the whole thing. Okay, it is our kind of a hypothesis or kind of a known knowledge. Okay, that pulse power supply will give you better results. But why? Let me just indicate here. Okay, so if you look at this case here, in case of a DC power supply, we are going to have a continuous thing. Okay, but when you say a pulse power supply, the current is on for some period of time and then it's off, then again on, then again off, right? So it means that what is happening here, that during the pulse on period, okay, material is taking place, material removal, right? And in off period, when we do not have any current on, the electrolyte flow is always on. Okay, so even though in the pulse off period the machining is not taking place, electrolyte flow is on, and that electrolyte flow will basically help in the removing of the sludge from the machining zone. Okay, however, in case of a DC, okay, there's no time which is available for purely for a sludge removal. It means that sludge removal is going to be more challenging in case of a DC continuous power supply compared to a pulse power supply here. Okay, and because of this particular reason, okay, we have seen that the pulse power supply is giving us a better results. Okay, some of the experimental observation is shown here. Okay, so if you look at this thing, okay, this is this gas bubble, hydrogen gas bubble, okay, which is basically are available here. Okay, now if you look at this this thing here, that in case of a DC power supply, okay, the bubble size is very large compared to a pulse power supply. Okay, so the volume of the bubbles which are formed when using pulse power supply, okay, they were relatively smaller compared to DC power supply. Okay, so in case of pulse thing, okay, bubbles are basically removed quickly, and electrolyte is also replenished. Replenished is that fresh electrolyte. Okay, fresh electrolyte is reaching to the machining zone, and sludge removal is more efficient compared to a DC. Okay, so pulse is definitely better than that. After that, we have investigated the pulse frequency. Okay, because when we talk about pulse power supply, okay, there are two important parameters. One parameter is the frequency, right? So for example, this is a on period, this is off period, right? Okay, so frequency means, okay, 1 by T on plus T off. That within a second, how many times cycles is running, okay, that is known as a pulse frequency. Another term is known as a duty ratio, okay, duty ratio, which is nothing but T on period divided by the total period. Okay, so we have investigated 1 kilohertz and 100 kilohertz. Okay, results were slightly better. Okay, if you look at this picture here, if you are going to use a higher pulse frequency, the results are slightly better, not that much difference, okay, as it is obvious in this picture, but there is slightly difference in case of a high frequency. So if you have a high pulse frequency available in your institute, I would personally recommend you to utilize and use this high pulse frequency to obtain a uniform dissolution in case of an area array 2 electrode. Okay, then duty ratio. Okay, so if you look at the duty ratio, if you have a low duty ratio, it means that off period is larger, right? Because duty ratio is nothing but on period divided by the on plus off, right? So if you have low duty ratio, it means that pulse on is shorter, pulse off is larger, right? So during the pulse off period, as I mentioned, that electrolyte will basically remove the sludge formation. So what we have seen and observed is that sludge removal is more efficient for a lower duty ratio. Okay, so given a choice, okay, especially for sludge removal point of view, lower duty ratio is going to provide you a better results. Okay, so if you are, so in summary, we can say that if you are going to utilize, okay, a thing, you have to use a pulse power supply, you have to go for a high pulse frequency with low duty ratio. If you do this thing, then you will get a more than uniform material dissolution. Okay, so let me summarize this thing quickly. Okay, so in this today's talk, I have mainly focused on the electrochemical machining process, okay, which is a relatively very low cost process, okay, but it can be utilized mainly for size reduction point of view. It can be used for surface roughness reduction point of view, okay, or if you want to create for example some kind of coatings, then also you can use this kind of electrochemical machining process. Okay, however, getting a controlled dissolution, I would say controlled and uniform dissolution, is not easy. Okay, there's a lot of challenge. You have to think about how the current lines are going to be distributed. Okay, what is the distribution of the lines in location dependent behavior. So all these things will come in picture. Okay, so beside the conventional current pulse thing, okay, you have to also look at the shape and size. These are two important things. Okay, and this is especially true for an area array and line array a two electrode point of view. So ideally, the size of the counter electrode should be exactly same. Okay, exactly same. But for many practical applications, for example, let's say that I am using a 3x3 tool electrode, right? Let me just example. I'm using 3x3, but the tip size is going to be 100 micrometer, for example, right? So 100 micrometer is going to tip size. Let's say that I am using a 2 times of gap. 200 micrometer is going to be the gap, right? So if you look at 100, 200, again 300, okay, 4, 6, 7. So this 3x3 area array is going to be 700 micrometer in total. So if you look at it from this length to this length, it is going to be 0.7 millimeter only, right? So ideally, from this point of view, if you are going to utilize a flat plate electrode, the counter electrode will have a size of 0.7 millimeter, which is an extremely challenging task, right? You have to make sure that you have to put this electrode just below that, right? If you put this counter electrode little bit away, then also you will have a problem, because if you put like this thing, okay, this line will have a lower resolution, this will have a higher resolution. Okay, so ideally the counter electrode has to be kept just below and the size should be the same. Okay, but it has a lot of challenges for practical point of view. That's why it is, if you have a requirement, if you cannot afford to go for a smaller size, then you can change the shape of the electrode. In that case, a spherical shape will give you better results. Okay. Then I have indicated here that low duty ratio and high pulse frequency are definitely better in order to get a uniform resolution rate. Okay. So finally, in my laboratory, we are utilizing these results to create glass micromachining of several applications. Okay. So with this, I like to conclude my talk. We have about 10 minutes time to answer your questions. Let me just stop thing here.
Sir, thank you so much, sir. Thank you so much for the talk, sir. I want to request the participant, if they have any question to ask, they can please ask.
Yes, that I would definitely encourage all of the participants, because this is a faculty development program, and the basic idea is just to interact. Okay, so if you have any sort of questions or any doubt, okay, related to the experiments, please feel free to ask me, and I will be happy to answer that.
Yes, sir. Definitely.
Hi, sir. Hello.
Yes, Mr. Vishnu. Yeah.
Sir, actually, I just need your view on the usage of hollow electrodes for this process. Is it possible? Like,
So hollow electrode for glass micromachining, or for which application are you talking about?
no, I'm generally asking for the electrochemical machining process, not particularly concentrating on certain areas.
Yes, I understand. Yeah. So, Mr. Vishnu, see, hollow tool electrode are definitely beneficial, especially because they allow the electrolyte to be flow from inside it, right? So they can be electrolyte flow, and sludge removal is going to be very, very challenging, very, very easy in this case, right? But when we talk about the micro machining application, where we are talking about tool dimension of 200, 300 micrometer, how will you create a hollow tool electrode in those cases? Okay. So to answer your question, that if the dimension of the workpiece, okay, or the dimension of the micro feature is large, then it is always a good idea to utilize this hollow tool electrode. Okay. But in case of micro machining application, okay, this will offer you more challenges, because hollow tool electrode, because they are not so mechanically stiff, right? So there are always chances of that this particular tool electrode will bend. Okay, so these are the one of the thing. Second thing is that, let's say that you want to create some kind of a blind cavity. Okay, you don't want to create some kind of through hole. So in those blind cavity, what is going to happen here, that you will have some kind of a some kind of feature which will not be etched away. So the surface is not going to be flat. Okay, so these are the two things due to which hollow tool electrodes are only applicable for those cases where the dimension is on the larger side.
Okay, sir, I got it. But why I asked this doubt was, sir, I just came across one of the journals claiming that sidewall, if you are giving sidewall insulations for the tool, with hollow structure, then it will be much more better, and it is giving little efficiency.
No, certainly, there is no doubt, right? See, one of the, obvious thing is that if you have hollow tool electrode, electrolyte, you can basically flow through the inside, and it will go to the machining zone and it will remove it, right? Okay. Second thing, what you mentioned about the passivation layer, that is definitely beneficial, because if you are using a side insulation, then you will not have any kind of a sideway machining. Okay, so the overall overcut is going to be smaller. So from those point of view, definitely there is advantage for using hollow tool electrode. But again, my question here is that, okay, for those micro machining application where we have to create, like I said, I told you 100, 200 micrometer, how will you do that? Second thing is that hollow tool electrode is okay for a single tip electrode applications, right? But again, if you have an area array, how will you do that? How will you create and arrange those hollow tool electrode in a area array fashion? So because of these challenges, things are not moving that much in case of a hollow tool electrode.
Okay, sir. Thanks for the information. Like, it certainly is a area of discussion which needs to be stressed upon, because
certainly, sir, please feel free to contact me. Okay, I would be happy to, because like I said, there are a lot of applications happening in ECM area, not on the traditional metal, but for example, electrochemical etching, right? For example, everybody is talking about electrical vehicles, right? In electrical vehicle, one of the major application area is supercapacitor, right? And for supercapacitor, we are talking about a porous material, right? Porous silicon, for example. And in order to create porous silicon, people are using electrochemical etching, which is very similar to electrochemical machining process. Fundamentals are same, only slightly different. So from those application area, those emerging area, this particular technology is having a lot of applications. Any other questions? Are there any other questions from the participant? I mean, this is a good time for you to, because this is the main objective of the FDP program. I'm a bit disappointed that participants are not really asking questions. I think they are not really fully fulfilling the main objective of this FDP program.
Sir, actually, sir, these topics are maybe new to a few of the participants.
Yes,
but that is why they have actually not much knowledge about this.
But this means
topics,
that if the topic is new, then there should be a lot of questions.
Yes, sir. Sir, purely based on the experimental data, sir, what you have told, that is purely based on experiment, what you have done. That is why I think so, sir. But sir, the talk was very informative, sir. And thank you so much, sir. Thank you so much once again for joining us and being a part of this FDP program.
Thank you. It was my really pleasure. So again, those who like to know about this process or detail, or those who wanted to visit my laboratory, okay, those who are looking for some kind of academic collaboration, please feel free to contact me. And this is what IITs are encouraging, that we want to set up some kind of academic collaboration with the other institutions. Okay, and we are always looking forward for good PhD students. So that is always you can contact me if you want to have PhD study with me or something. Okay.
Sir, one more thing, sir. This is Vishnu, sir. Actually.
Yes, Vishnu, please.
Sir, actually, you told me like you just share your lab setup and everything. So I just went through the photographs and also, is it possible that our students is it possible for our students to carry out projects and extended studies on that?
Yes. It is very much possible. The only thing is that in Mumbai you have to arrange your own accommodation.
I know, sir. I know because I was working in Mumbai for the past 2 years.
So out of the existing IIT Delhi and IIT Bombay, these are two IITs who do not have any landscape. And it is earlier there was this kind of a program where we were asking the other researchers to come and stay in the campus. But right now, because of the growing number of students and the limited hostels, it is extremely challenging even for our own students to stay in the campus. So as long as you have this accommodation issue sorted out, I think you can definitely visit and work with us. In fact, we will be happy to share all these kind of things. Yeah,
okay, thanks, sir. I'll just speak with my students. If anyone is interested in this particular field, then I'll definitely contact you, sir. I have your contact number. I'll get in touch with you.
Very nice. Okay.
Thanks, sir. Thanks. Bye.
Thank you very much. Yeah. Anybody else has any question? Right. Fine. So if you do not have any question, then I will excuse myself. Okay. I need to rush for another meeting. Okay. So thank you very much.
Thank you so much, sir. Thank you.
Thank you.
Sir, namaste.
Namaskar.